All right, we are beginning chapter 9, and we are going to be talking about sequences and series for the next several weeks. And let's just first start out by comparing the relationship between sequences and series. Just so you know that after today, the majority of what we're going to be studying is going to be related to series as opposed to sequences. And so if you notice here, a sequence is nothing more than a list of terms. It's just a list of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10, 12. Those are list of even numbers. 1, 3, 5, 7, 9, 11. List of odd numbers. 1, 4, 9, 16. Those are the list of perfect squares. And so that's all a sequence is. And so an example would be a sub n is equal to 2 to the n, and n is the term number, and it normally starts at 1. So a sub 1 would be 2, and then 2 squared is 4, and then 2 to the third is 8, and you can figure out the pattern from there. Now a series, which is going to be the majority of our focus over the next few weeks, is the sum of the list of terms. And so we'll say S1, which is the sum of the first term, is just 2. And then the sum of the first two terms would be 2 plus 4, which is 6. And then the sum of the first three terms would be 2 plus 4 plus 8, which would be 14. And then the sum of the first four terms would be 2 plus 4 plus 8 plus 16, which would be 30. And so we're going to get into series a little bit more, but today we're going to focus on sequences. So the first problem says write out the first 5 terms of the following sequences. So this should be pretty simple for us. A sub n is equal to 3 to the n. That's our first sequence. And so A1 is going to be 3 to the first. And then A2 is going to be 3 to the second, which is 9. And then A3 is going to be 27. A4 is going to be 81, and A5 is going to be 243. All right, so then it says the second sequence they want us to write out the first 5 terms is A sub n is equal to 2 over n factorial. Let's talk about what a factorial is. You may or may not remember from pre-cal, but a factorial is simply a number times all the numbers that came before it. So 5 factorial would be 5 times 4 times 3 times 2 times 1, which is equal to 120. All right, so if we want to write out the first 5 terms, a sub 1, and 1 factorial is 1. 0 factorial is also defined as 1. But this is asking us for a sub 1, so 2 over 1, that is 2. And then A2 is going to be 2 over 2 times 1, which is 1. And then A3 is going to be 2 over 3 times 2 times 1, so 2. And actually you can cancel these 2's out, and this ends up being 1/3. And then A4 is going to be 2 over 4 times 3 times 2 times 1. And so the 2's can cancel out, and you are left with 1 over 12. And then A5 is going to equal 2 over 5 factorial, so that's going to be 2 over 120. And that's just going to be 1 over 60. And so that's how you write out the first 5 terms. All right, in this next example, they want us to write an expression for the following sequences. So they are now giving us the numbers, and they want us to write the expression. And so first one is pretty simple. This is called an arithmetic sequence. And an arithmetic sequence is simply a sequence that, so let me write this down here. An arithmetic sequence is one that you are adding the same number each time. So you're adding common difference. And there are also other sequences, and another one that we want to be familiar with is a geometric sequence. And that is when you are multiplying by the same ratio. So these both have formulas. This one, the geometric one, a sub n, is going to be equal to the first term in its sequence times r to the n minus 1. And then the arithmetic one is going to be a sub n is equal to the first term plus the common difference times n minus 1. And if you know these formulas, it makes it pretty simple to write the expression out for the arithmetic and geometric. You don't have to think very hard about it. So going back to letter A, we can see that you're adding 5 each time. So our A1 is 3, that's our first term, and our D is 5. So that makes it pretty simple to write this out. A sub n is going to equal 3 plus 5 times n minus 1. And if we distribute this 5 in here, we will get 5n minus 5 plus 3. So A sub n is 5n minus 2. All right, so letter B does not fit into either category. It's not arithmetic because you're not adding the same amount. It goes up by 3, then up by 5, then up by 7, then up by 9. You're also not multiplying by the same ratio each time. You can see that to go from 1 to 4, you're multiplying by 4, but then you're not multiplying by 4 anymore. So this is just one you have to look at and realize it's the difference, excuse me, not the difference, but this is the list of perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth. So A sub n is going to be n squared. All right, so the first two are pretty basic. And then letter C is one where you're going to have to think about a little bit. And if you look at the numerators of all of these fractions, you'll notice that they are one number smaller than the powers of 3. If we start and we say 3 to the first is 3. 3 squared is 9. 3 to the third is 27. And if you subtract 1 from each of these, you get 2, you get 8, and you get 26. So the top looks like we could write it as 3 to the n minus 1. Now make sure you don't put the minus 1 up here with the n. It's 3 to the n minus 1. So there's our numerator. And we'll call this A sub n. And if you look at the bottom, well, you have 1, and then 2, and then 6, and then 24, and then 120. Well, we've seen 120 before on the last slide. That was 5 factorial. And this looks like 4 factorial, and then 3 factorial, then 2 factorial, and 1 factorial. So therefore, the bottom just looks like it's n factorial. Now, you may think you're done, but I want you to notice something here, that the numbers are oscillating in their signs. The first number is negative, and then the second is positive, then negative, then positive, then negative. Anytime you have that situation, you need to put out in front a negative 1 to the n power. And always check and make sure that when you plug n back in, it gives you this list. So let's just start off with when n is 1. So we'll say n equals 1. So when n is 1, you get negative 1 to the first power, which is negative 1. And then 3 to the first is 3 minus 1 is 2. And 1 factorial is 1. So we end up getting negative 2 over 1, which is the first term. And so you can assume that's going to work for the rest of those as well. So now we're going to talk about how to determine whether a sequence or a sequence either converges or diverges. And so let's talk about what those words mean. They're pretty simple concept to understand. A sequence will converge if the numbers in the list are approaching a finite value, a finite number. All right, so let's say we have the numbers 4, 2, 1, 1/2, 1/4, 1/8, 1/16, 1/32, comma, dot, dot, dot. Well, those numbers, if I keep going, are approaching 0. So this would be an example of a sequence that would converge. Now, if I flip those numbers around and I start going the other way, 1, 2, 4, 8, 16, 32, 64, comma, dot, 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 well, the numbers are getting bigger and bigger, and the further I go on this list, the numbers are not approaching a finite value, so that would be an example of a sequence that would diverge. Right? So there are couple of different ways that a sequence could actually diverge. One would be if it is approaching infinity, and another way would be if it is oscillating between numbers. So for instance, like a cosine curve. Well, it starts up here, then it goes down, and then up, and then down, then up, and then down, and then up, and then down. And as the angle gets bigger and bigger, it never flattens out to a specific number. It just keeps oscillating between numbers. So in that case, you would say that that would diverge as well. So in this first example, letter A, we can see that the numbers are going down, and it wants us to determine whether each sequence converges or diverges. If it converges, then find the limit. In other words, tell us what number it's heading towards, what is it converging to, and if it diverges, explain why it diverges. And letter A, we can see once again the numbers are getting smaller and smaller and smaller, and so eventually this is going to converge to 0. So we'll put converge to 0. All right, letter B, a sub n is equal to 3/5 to the n power. So let's just start writing out some terms here. A sub 1 would be 3/5. And then we're going to multiply, so 3/5 squared is going to be 9/25. And then we're going to multiply by 3/5 again. And let's see, 9 times 3 is 27. And 5 times 25 is going to be 125. So you can see where these numbers are going. Once again, the more terms you write, the more they are going to converge to 0. Now this is a geometric sequence, and so one of the things that we want to recognize is that anytime you are multiplying by the absolute value of any number that is less than 1, doesn't matter if it's positive or negative because it's absolute value, then it's going to automatically converge to 0. All right, because the numbers are going to be getting smaller and smaller and smaller. And eventually, when you multiply by numbers smaller than 1, eventually, it may take longer, but eventually it's going to get to 0. All right, letter C. The opposite is true. Here we're multiplying by a number bigger than 1, and so this is going to diverge because the numbers are approaching infinity. All right, continuing, we still want to determine whether each sequence converges or diverges. So here we have 5 different sequences, and the first one, a sub n, is equal to the sine of n. Well, we kind of looked at this one a little bit before, but if we were to graph the sine of x, would look like this. And so as the angle approaches infinity, the value of the sine function does not approach a particular value. It just oscillates between 1 and -1. So this is going to diverge. And the reason is because it oscillates. So you will say it oscillates and it diverges. All right, the second sequence. Let's just write out a few terms here. So when n is 1, you will have 3 plus -1, which is 2. When n is 2, you will square -1 and get +1, and then you'll get 4. And when n is 3, it'll be -1 to the third power, which is -1, and you're going to get 2, and then 4, and then 2, and then 4. So this is going to diverge for the same reason. Okay, now the third one is maybe not so apparent here, but you can see that as n gets bigger and bigger and bigger, well, you're going to have infinity over infinity. And so the question is, well, what's going to happen to this overall number, natural log of n over n? Well, this actually takes us back to something that we did a couple weeks ago, which is the L'Hopital's rule. And so we get an indeterminate form here, and we can take the derivative of the top, which is 1 over n, and the derivative of the bottom, which is just 1, and then we can say the limit as n approaches infinity of 1 over n. Well, if we plug infinity into the bottom, we're going to get 1 over infinity, which is 0. So this is going to converge to 0. Now, we also could have just taken a look at this and seen that natural log curve looks like this, and the linear function looks like that. And so the linear function is going to grow much quicker than the natural log function. And so therefore the denominator is going to always be, as n gets bigger, is going to be much bigger than the numerator, and eventually the numbers are going to head to 0. Okay, so the fourth one and the fifth one involve factorials. And these ones you have to be careful with here. Let's review a factorial. It's going to be a number times all the numbers that came before it. So on the bottom, we have to get a little clever here. We can write n plus 3 factorial as n plus 3 times the number that came before n plus 3, which means you would subtract 1 from that number, which would be n plus 2. The same way you would do 5 factorial. You would start with 5, subtract 1, multiply by 4, subtract another one, multiply by 3, subtract 1, and so on and so forth. Well, same thing is true here. So we're going to subtract 1 from n plus 2, and we're going to get n plus 1. Now, we don't want to go forever and keep subtracting 1, so we can just write this last part as n plus 1 factorial. And make sure you convince yourself in your own mind that that makes sense. N plus 3 factorial is going to be n plus 3 times the number that came before it, n plus 2, times the number that came before it, n plus 1, times the number that came before that, on and on and on, all the way down to 0. Well, the top is going to be n plus 1 factorial. We're going to leave that alone. And we can see that there's an n plus 1 factorial on the bottom, and there is an n plus 1 factorial on the top. So these two are going to cancel, and they are going to leave us with 1 over n plus 3 n plus 2. And so now we're going to say, well, as n approaches infinity, well, it's very clear now that the bottom is going to be really big number. So you're going to have 1 over infinity, which is going to converge to 0. All right, same type of situation in the last example, and it's going to be n plus 1 factorial. So we're going to write that as n plus 1 times the number that came before it, which is n, times the number that came before that, which would be n minus 1, and then n minus 2. And we're going to capture all the rest of those numbers by just writing n factorial. And then on the bottom we have n factorial. And so we can see that the n factorial on the bottom and n factorial on the top cancel, leaving us with n plus 1 on the top. And so now if we take the limit as n approaches infinity of n plus 1, well, that's just equal to infinity. And so because we got infinity, this is going to diverge. All right, in the last example, we're going to talk about the squeeze theorem. And the squeeze theorem basically says that if you have a sequence that is sandwiched, and sometimes it's called the sandwich theorem, it is sandwiched between two other sequences, and you know what those two sequences do, then by definition, or by default rather, that this sequence will converge to the values that it's sandwiched between. So let's just say that we know that the cosine of n is always going to be between -1 and 1. So we know that because we know what the graph of cosine looks like. All right? So why don't we say, we'll make a little number line and we'll say -1, say 0, we'll say 1. So this represents the cosine of n. Now, cosine squared of n, well, if you take any of these negative values for cosine and square them, they are going to become positive. If you take any of the positive values of cosine and square them, they will stay positive. So the cosine squared of n, you could say, is always going to be bigger than 0, greater than or equal to 0. So we'll say cosine squared of n is always going to be greater than or equal to 0. Why do I keep doing that? Cosine squared of n is always going to be greater than or equal to 0 or less than or equal to 1. All right, so now what we're going to do is we are trying to analyze what cosine squared n over 2 over n is going to do, 2 to the n. So we're going to divide each of these by 2 to the n. Divide by 2 to the n, and divide by 2 to the n. Well, 0 divided by 2 to the n is just going to be 0. And cosine squared of n over 2 to the n, we'll leave that alone. And then over here we have 1 over 2 to the n. Well, if we just take a look at this and say, well, as n approaches infinity, well, y equals 0 is just going to be 0. So let's just say this will converge to 0. And 2 to the infinity is infinity, so 1 over infinity, well, that's just going to converge to 0. And so if the left function converges to 0 and the right function converges to 0, then the function that is sandwiched between them will, by default, converge to 0. And that is the idea of the squeeze theorem.